Hello everyone and welcome back. My name is Mr. Kovald, and in this video I'm going to be going over the second situation in which a reaction wants to go to 100% completion before equilibrating. So in this second situation, or let's remind ourselves about the first situation. The first situation is where we had a large K value and the shift was towards the favored side. And in that way, we saw that whenever you have the shift towards the favored side, you can't assume that X is going to be negligible. You can't use that tool or that strategy. So, in what you're going to have to do first is do a stoichiometry table, an ICF table or IF table or whatever you want to call it. But you have to do stoichiometry first. You assume that it goes 100% towards the favored side, and then figure out what your limiting reactant is going to be. So that one's going to go to completion, or that's going to go to zero, and then so you can figure out the change. Then from there, figure out what the rest of the final number of moles are going to be for all your species, and then use that to figure out what your initial concentrations are for your ice table. So you do a stoichiometry table first, followed by your ice table. So in this situation, instead of starting with a problem where K is large, you have a K that is small. But the strategy is still the same. So here you have a very small K value, and it's going to shift towards the favored side. And because it's shifting towards the favored side, you can't assume that X is negligible. So you got your stoichiometry first, and then your ice table. So here is the problem. I have zero amount of reactants to start with. I have a 0.6 molar of product C, and I have 0.3 molar of product D. And so I look at my K value, and you'll see that it's very, very small. And so what that means is you're going to have a lot of reactants. So I got to change this. So this is flipped. So because this is very small, remember that means you have a very large denominator and the reactants are on the denominator. So you have a lot of reactants and you have a few products. So this equilibrium is favoring the reactant side. So reactants are very much favored in this reaction. So this is going to want to go this way, very much so, such that almost all of this is going to be gone, right? It's going to try to get rid of almost all of this. Is it going to get rid of all of it? No. So we know it's strongly in this direction, right? So it favors this side. But we also notice here that we have zero reactants. So we know that it's going to shift in this direction. So it's shifting towards the very favored side. So because it shifted this way towards the favored side, we cannot assume X is going to be negligible. Actually, X is going to be very large compared to these starting molarities, starting concentrations. So we can't do X is negligible, so you have to do a stoichiometry table first. So remember, when you do a stoichiometry table, you cannot start with molarities. You have to change the molarities to moles. So, but for the sake of this problem, for the sake of making this simple, we're going to assume that we have 1 liter of solution so that our molarities are the same as moles. So we'll get rid of the molarities. Excuse me. So we'll get rid of the molarities and we'll have moles. So we have 1 liter of solution. Now for your problem, if you have 2 liters of solution, if you have something that's not 1 liter of solution, then you'll have to do the calculation to find the moles of each of your products and reactants. Okay, so we have our moles. First thing we want to know is which one of these is our limiting reagent, which one of these is going to go away first. So I know that I have a 1-to-3 ratio. So for every one of these, I need 3 of these to react. So I need 3 times as much. So if I have 0.3 moles of this, then I need 3 times as much of C. So 0.3 times 3 is 0.9. So I need 0.9 of this, but I don't have 0.9. I have 0.6, so I don't have enough. So this is going to go away first. That's my limiting reactant. So this is going to go to 0. So I'm going to lose 0.6 for the change in my ICF table. And then that's going to go to 0 for my final amount. So if I lose 0.6 of this, I'm going to lose 1/3 amount of this. So 1/3. So if for every one of these, I lose 1/3 of this. So I'm going to lose 1/3 amount of this. So 1/3 of 6 is 0.2. So I'm going to lose 0.2 moles of that. And I'm going to end up with 0.1 moles left over. And again, if I lose 0.02 moles of this, then I'm going to lose I'm going to gain a double amount of that because it's a 1-to-2. So if I lose 0.2 here, I'm going to gain a 0.4 moles here. And so I'm going to end up with 0 plus 0.4. I'm going to end up with 0.4 moles of B. And again, since this is a 1-to-1 ratio, if I lose 0.2 moles here, then I'm going to gain 0.2 moles. Oops. That should be moles here. So I end up with a 0.2 mole amount here. So let me double check to make sure I didn't make any mistakes. So I lose 0.6 moles here, go to 0, right? Because I start with 0.6. This is my limiting reagent. I lose 0.6 to go to 0. So this is a 3-to-1. So if I lose 0.6 here, I lose 1/3 of that amount here, which is 0.2 moles. So I subtract 0.2 from 0.3, I get 0.1 moles. And then because I'm losing, since this is a 1-to-2 ratio, I'm losing 0.2 moles here. I'm going to gain double that amount here. So I gain 0.4 here. So I end up with 0.4 moles. And since this is a 1-to-1, right, A and D are 1-to-1, if I lose a 0.2 moles here, I'm going to gain a 0.2 moles here. So I get that. Okay, so now I have my mole amounts. So now I have to convert that back to molarity. Now for my problem, I'm assuming that I have 1 liter of solution. So the numbers of moles are going to be all divided by 1 liter, which gives me the same number in molarity. For your problem, it might be 2 liters. It might be 1.5 liters of solution. Whatever the liters are, you have to divide your moles by that number of liters to get it back to molarity. Again, you can't use moles in ice tables unless you got some special circumstance like 1 liter of solution or something like that. So I divide everything by 1 liter, 1 liter, 1 liter. I get the same numbers. So my initial molarities now for my ice table are going to be what I have for the final divided by the liters of solution. So I have 2 molar to start with for A. I have 0.4 molar to start with B. I have 0 to start with C. And I have 0.1 molar for D. So now I have my initial conditions, and you'll notice now for my ice table, I have a 0 for a product, which means that it's going to shift towards the products, right? If you do your Q calculation, you'll get 0 for Q, which will then tell you that it's going to shift towards products. So it's going to shift away from the favored side. So now you know, now that it's shifting away from the favored side, you know that it's going to shift a little tiny bit. So now you can do the x is small approximation. You can neglect x. So now we can do our x. So here we have, we're going to shift this way. So this is going to be a minus x. This is going to be minus 2x. This is going to be a plus 3x. And this is going to be a plus x. And so now my equilibrium expressions are going to be 0.2 minus x. This is going to be 0.4 minus 2x. This is going to be 3x. And this is going to be 0.1 plus x. So now I can write out my K expression. So it's going to be D, concentration of D, multiplied by the concentration of C raised to the power of 3 because of the 3 coefficient, divided by the concentration of B raised to the power of 2 because of the 2 coefficient, and multiplied by the concentration of A. So now I can put in my equilibrium expressions in terms of x. So D is 0.1 minus x, 0.1 minus x. C is 3x, so that's going to be 3x cubed. And I have B, so B is 0.4 minus 2x squared multiplied by A, which is 0.2x minus x, 0.2 minus x, sorry, 0.2 minus x. Okay, so now, since I know that x is going to be very tiny compared to the initial concentrations, 0.1, 3, 0.2, then I know, or not 3, I'm sorry, the 0.4, I can eliminate or neglect x. So I'm going to get rid of x here. I got to keep that x because I'm not subtracting it from anything. So then what this becomes, simplified, so 3 cubed is 27. That's going to be 27. So then multiplied by 0.1. So I'm going to have 0.1 multiplied by 27x cubed over, I'm going to have 0.2. So I'm going to have 0.4 squared multiplied by 0.2. And so now I have a very simplified version of my x cubed function. Now, if I started to try to do an x is small approximation here, if I tried to do an ICE table with the original amounts, I would have gotten an equation very similar like this, where I would end up with an x cubed or x to the 4th power that I was not going to be able to solve very easily at all. So if you ever run into a problem like that where you get this really ugly monstrosity of an equation or problem that has you to the x to the 4th or 5th or 3rd or something like that, you might want to double check to make sure that maybe you should do a stoichiometry table first and then do your ICE table. Okay, let's continue. So if I complete this here, I can simplify this. So I can take 0.1 multiplied by 27 and then divide that by this and divide it by this. So let's go ahead and calculate that. Okay, so when I calculate this out, I end up getting, what I get, 84,375. So I get 84.375 x cubed times x cubed. So now I can set this equal to k, right? So this is equal to KEQ, and my KEQ is 2 times 10 to the negative 26. So now I have 2 times 10 to the negative 26, and that's going to be equal to 84.375 x cubed. And now I can easily, on my calculator, divide both sides by 84. So I can divide this by 84.375, and then I can take the cube root of both sides, and I get x. And when I do that, I get x is equal to, hold on a second. And so when I calculate this out, I get x is equal to 6.18879 times 10 to the negative 10. Okay, you don't need to keep all those digits. All right, so that's my x value, and you can see that x is really, really small as we predicted by this shift. So you can see that this is going to be very small compared to 0.4, 0.1, and 0.2. So definitely, if you do if you check with the 5% rule, if you divide this by any of these values, 0.1, 0.4, 0.2, you're going to get a percentage that's much, much less than 1. So it's going to be valid. So you don't really have to check here. It's quite obvious it's going to be valid. But if you want to, you could check that. Now that I have my x, I'm going to plug x into each of these expressions to find the equilibrium concentrations of all of my species at equilibrium. So, and that's how it's done, ladies and gentlemen. So I hope this was helpful. And again, the rule of thumb is if you have a K value, whether it's small or large, if the shift of the reaction is towards the favored side, you're going to have to do an stoichiometry table first, and then using moles. And then once you get the final moles after making everything go to 100% completion, then you got to convert that to molarities and then do an ice table with molarities. If you do that, you'll be sure to be able to use your x is small assumption. You can neglect x, get rid of it, and simplify your calculations, and therefore simplify your life in chemistry. So I hope this was helpful. If you enjoyed this video, if this helped you in any way, then please like the video, hit the like button over there or somewhere, wherever it is, find it, like it, and also subscribe to my channel, hit that notification bell. When you do, make sure you select all so you can be notified by all the videos I put out. And then finally, put a comment down below. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me, and have a great day.